This short video dives under the hood to show how AWS AI services connect. We've used Bedrock, Textract, Lex, and step functions, but this video reveals the underlying architecture. Understanding this allows you to design your own pipelines from scratch, not just follow tutorials. This program is brought to you by the Series of Thoughts team as part of the AWS and Cloud Foundation Series Module 4, Episode 6.
This video covers how services connect, focusing on data formats, permission boundaries, and failure modes. We will look at the event-driven pattern, data formats at each stage, IAM in AI pipelines, error handling, and a full pipeline visualization. Chapter 1 covers the event-driven architecture pattern. Virtually every AWS AI integration follows a 4-beat rhythm. An event fires, a function invokes an AI service, the service returns a result, and that result triggers the next step. Mastering this pattern is key for new pipeline variations. The Universal AWS AI loop consists of 4 repeating stages: event trigger, Lambda invocation, AI service call, and result routing. Architecting new pipelines involves substituting services within these 4 beats. This is the actual execution model for production AI pipelines. Event sources pull the trigger for the pipeline. Common triggers include S3 object creation, API gateway requests, SQS messages, or event bridge schedules. Choosing the right trigger determines the pipeline's latency, cost, and reliability. S3 is common for document A. I like Textract. Lambda is the orchestration glue, serving as a payload transformer and permission broker. It transforms the incoming event, calls the AI service using execution role credentials, and routes the response. Remember the 15-minute execution limit. For long-running tasks, use asynchronous patterns like step functions callbacks. Chapter 2 focuses on data formats at each stage. The most common source of bugs is a JSON shape mismatch between services. Understanding the exact payload structure at each boundary is crucial for robust production pipelines. Textract's Analyze Document API accepts a JSON request body, preferably with an S3 object reference in production, to avoid Lambda payload limits. Use the S3 reference for asynchronous processing of multi-page documents. Decide on feature types carefully, as requesting tables and forms increases processing time and cost. Textract outputs nested JSON blocks, like key_value_sets. The Lambda function flattens this structure into a clean key-value map for downstream services. This is a critical transformation stage to simplify the data. Step functions manages the pipeline state using a state machine model. Each state processes a JSON input, performs an action, and outputs JSON for the next state. The entire pipeline data evolves within this shared state object. Bedrock's Invoke Model API requires a model-specific JSON body serialized as a byte string. Always consult the model's documentation, as schemas vary. Crucially, the body field must be a JSON-encoded string, which Lambda must serialize before invocation. Tracking the payload JSON at every stage boundary is the most effective debugging technique. For the invoice workflow, the payload evolves from S3 metadata through Textract and Lambda transformations to structured data for Bedrock, leading to conditional routing and final output. Chapter 3 covers IAM, the permission layer in AI pipelines. Every service-to-service call requires an explicit permission grant, even within the same AWS account. IAM roles and policies connect services like step functions, Lambda, Bedrock, and S3. Incorrect IAM configuration is a common cause of runtime failures. Each service assumes a distinct execution role with a trust policy and permissions policy. This enforces the principle of least privilege. Examples include step functions needing permission to invoke Lambda and Bedrock, and Lambda needing permissions for Textract, S3, DynamoDB, and logs. Best practice for IAM policy is to apply the principle of least privilege in practice. Use customer-managed inline policies scoped to the exact actions and resources needed, such as granting Lambda read access only to a specific S3 bucket prefix and the necessary Textract and Bedrock actions. IAM uses 2 policy types: identity-based role policies and resource-based policies. Role policies control what a service can do. Resource policies, attached to the target resource, control who can access it. Both policies must permit the action for cross-service calls to succeed. Bedrock adds an extra permission layer. Model access must be explicitly enabled in the Bedrock console, separate from IAM. For Lambda running in a VPC, a Bedrock VPC endpoint is also required. You must pass all three gates, IAM, model access, and VPC endpoints, for API calls to succeed. Chapter 4 covers error handling in production AI pipelines. Production pipelines fail in unexpected ways, such as corrupted files, schema mismatches, or throughput limits. Step Functions provides precise, declarative tools for anticipating and handling every failure mode. Failures fall into three categories: transient failures, which are safe to retry; data failures, where input is malformed and requires human review; and logic failures, where the service returns a result, but code fails validation, requiring structured fallback. Step Functions retries are configured per state using the retry field. This defines error classes to catch, max attempts, the initial wait interval, and the exponential backoff multiplier. This declarative configuration removes retry logic from application code. The catch block routes failures when retries are exhausted. It enables graceful degradation by directing specific error classes to dedicated handler states, like a human review queue or a dead letter queue. This keeps the main workflow clean. Foundation models may not return structured JSON. Prompt engineering helps enforce output schema, but schema validation in Lambda is the last line of defense. Use structured output APIs like Bedrock's Converse API or Claude's tool use for deterministic data extraction. Every production pipeline needs a dead letter queue for terminal failures. The DLQ, typically SQS, preserves the payload for forensic analysis. A Cloud Watch Alarm on the DLQ depth provides immediate operational alerts. Use message redrive to replay messages after fixes. Chapter 5 is the full architecture walkthrough. With individual components understood, we now assemble them into the complete invoice processing workflow, showing every service, transformation, and permission boundary in one annotated architecture. This diagram visualizes the full pipeline, from invoice upload to outcome routing. Each arrow is an API call, governed by IAM, and each boundary is a potential failure point. Data transformation occurs via explicit Lambda functions at key stages. This table maps each service to its execution role, required permissions, and scoped resource. Use this as a reference for structuring your own pipeline's IAM configuration, ensuring least privilege access for step functions, Lambda, Textract, and Event Bridge. Atomic data transformation is essential. Each Lambda function is responsible for one task: converting S3 events to Textract requests, Textract blocks to key value maps to Bedrock prompts, and the final Bedrock response to a DynamoDB item. The step function's choice state serves as the pipeline's decision engine, routing execution based on conditional evaluation of the state JSON, such as a confidence score. All routing logic belongs here, not in Lambda code, and a default state is critical. AWS X-Ray provides distributed tracing across the entire pipeline. Enable X-Ray on step functions and Lambda to get a flame graph, seeing latency and errors at each stage, including Bedrock's invocation latency. The service map visualizes the complete live pipeline. Textract offers synchronous and asynchronous modes. Synchronous is for single-page documents under 5 megabytes and is suitable for real-time. Asynchronous handles multi-page PDFs and requires an external callback mechanism, often using step functions' wait-for-task token pattern. The wait-for-task token integration pattern handles Textract's asynchronous processing. Step functions pauses execution and embeds a unique token in the Textract job. When Textract finishes, an SNS-triggered Lambda uses this token to resume the step function's execution, eliminating polling. Architectural decisions significantly impact cost. Key cost drivers include Textract feature selection, Bedrock token consumption, step function state transitions, and Lambda duration. For example, simple text detection in Textract is 10 times cheaper than using forms and tables features. Avoid common anti-patterns like chaining Lambda directly, which causes fragile timeouts. Instead, use step functions, or SQS, between Lambda functions. Never hard-code credentials. Use IAM roles. Always validate raw AI output with schema, and use narrow, least privilege IAM policies instead of broad managed policies. The most valuable insight is architectural composability. The invoice pipeline is an instance of a universal event-driven pattern. You can swap Textract or Bedrock for other services, and the core structure remains identical. You are learning a reusable design vocabulary. 4 core patterns cover most production AWS AI pipelines. The event invoke route is the atomic unit. The async callback uses wait for task token for long-running jobs. The retry plus catch plus DLQ handles all failures. The least privilege role chain enforces security. Key takeaways include recognizing the universal loop pattern. Remember that data formats are the true integration layer. IAM is a correctness requirement, not just security plumbing. Finally, let step functions handle retry logic and error routing, keeping your Lambda code clean. This mental model allows you to design new AI systems by substituting services based on 4 concepts: event propagation, payload transformation, permission delegation, and failure isolation. This is the difference between implementing features and designing scalable systems. Up next in Module 4, Episode 7, we will look at 5 real AWS AI use cases for small businesses, complete with actual results. You'll see how the patterns from this video play out in production environments with real-world constraints.